before, we got two parts to this, and this first part isn't very hard again. I mean, you're finding this chapter much more relaxing, so to speak, than the other one, right?
Yes. Yeah, this was about
okay. This today is kind of new, but it's not hard to understand. It does, you'll start out kind of slow until you really get rolling, then it's going to go fast for you. And we've split it in half, which means the very first assignment is 17 questions. And it won't take me that long to explain it. So, anyway, 6.4, the title of it is called Polar Coordinates. And what it is a new way of expressing points on a two-dimensional grid. It's a new way that doesn't talk about how far out you go and how far up you go or down. It's about how long the vector is that you spin a certain angle. Okay, so in rectangular coordinates, we're used to seeing things this way, x, y, where this is the horizontal move from the origin, and then you plot that point. We're still going to be plotting points, but ours are going to be r theta. This being the length of the vector that we're spinning, this being how far we're going to spin it. And we will spin our angles from the positive x-axis counterclockwise like usual. Okay, and for the most part, I would say that not always, but for the most part, our angles will be in radians, but there may be some in degrees as well. The radius is the length. So if we were to take a look at a grid that had polar coordinates on it, and somebody published a bunch of empty grids for you to graph on, I'm not going to do that. Then we would have, it would have this these crosshairs right here, but we would have circles. That's a radius 1 having to do with that. So if the vector is 1 long, it would follow this path as we rotate it. Right? And then there's going to be another circle, another unit out, going around like that. So pretty soon you've got what looks like a target, and this would be a polar coordinate grid. And for example, if I had the point 3/4, I would go out 3 and spin that halfway through the first quadrant. That point right there is on that circle with radius 3, and that is the point 3/4 written in polar form. Guess what point it is rectangularly?
What's the other one? 3, 3.
3 root 2 over 2. 3 root 2 over 2. Because this is a 45, 45, 90 triangle, and the rectangular coordinates would be out this far. This is out a radius of 3. Is 3 times what the normal 1 would have been, which is root 2 over 2, root 2 over 2. So this is 3 root 2 over 2. And this is 3 root 2 over 2 because of the length of the radius. So this point right here is out that far, up that far. Corresponds to this. Rectangularly, we call it rectangular coordinates. Can you kind of see how they correlate a little bit? Okay, we're not going to have a bunch of circular things like this, but the circles are nice because it maintains the radius all the way around this R part of it, and then you spin a theta. We're still going to just use crosshairs, but we're going to pay attention to how long this is, and what we're going to do, instead of having 3 circles out here, we're just going to erase those circles and put a 3 right there, the length of the radius, which is the hypotenuse. It always has been. But it's not just going to be 1. We're used to unit circle stuff. This is going to expand farther into circles that are radius whatever. Okay, so that's a brief introduction. There is always, it seems like, when we do something new, there's always a hiccup that makes people have to stop and think a little bit. I want you to look at the pictures in the middle of page 534. Are y'all there? Because here comes the weirdness. You all know what happens when theta is negative, right? You open it clockwise. But what if r is negative? And it is often negative. You go, what do I do with that? You go through, by the way, polar coordinates, they call this point right here, in rectangular coordinates, we call this the origin. Polar coordinates, we call it the pole. Yeah, it's the pole where we rotate things around. And so to have a negative radius means you pretend it's positive, spin the angle, go out that far, and then you backtrack from whatever point you're on through the pole to the other quadrant exactly opposite of it, 180 degrees. That makes a radius negative. So If that doesn't make any sense to you, take a look at an example, maybe it will. On the very first one, notice the radius is not negative. It's 2 pi thirds. And so what's really also really weird is, in rectangular coordinates, you're used to taking this coordinate first and going out horizontally and then up. When you do polar coordinates, you generally spin this angle and then put this on it to indicate how long it is. So you usually spin the angle first. Okay? So in the first one right there, it says the angle is pi thirds. So we spin an angle pi thirds, which is 60 degrees. We draw a line that we call 2. And then at the end of that line is the point, the polar point, 2 pi thirds. Just that hard. See what's going on? Or not? In the next one, the point is -1, 3 pi fourths. So we spin the angle 3 pi fourths. And if that were a -3 pi fourths, we would spin it backwards. So we go to the angle, whatever sign it has, we spin it in the appropriate direction. So we spin out 3 pi fourths. We go out 1 unit on that line, and then you backtrack through the pole 1 unit and end up in the 4th quadrant instead.
So when you do these, like for the length, it's not necessarily like the actual length of the thing. Does that make sense? Because you just pull it back one, but it keeps going through. So this is just a continuous line.
Yeah, it's just the line. It's just the terminal side of the angle, and then you go out on that when you're done spinning it, like on 3 pi fourths. You go out what you consider to be 1 unit. Whatever that is, backtrack that same unit through the pole into the 4th quadrant and put that point there. Okay? So let me show you how I would do this on angle for the people that are watching. If we have, it was -1, 3 pi fourths. So this is a positive angle and a negative radius. That seems awful to have a negative radius, but this is how we deal with it. First of all, spin the angle. If, like I said before, if this had been negative also, we would have spun it this way. So we're gonna, but it's positive, so we're gonna spin it over here. That's the terminal side, and I made it extra long on purpose. That's the terminal side. Go out on that, whatever you feel like 1 unit is. I don't care what it is. But then backtrack through the pole the same distance on that line. That right there is the point. You see how it goes? Okay. So, and then it wouldn't hurt to put a 1 here maybe, and then a negative pi fourths here, because that's what that is. Just to indicate you know what you're doing. You don't have to put that on there, that's fine. If you show this whole thing right here, and it would, maybe you put a little X there, because it's not the point, but maybe put a little X there to indicate that you backtracked through there the same amount and plotted that point. Something like that, to indicate you know what you're doing. The author didn't do that, so whatever. As long as you get the point in the 4th quadrant, 1 unit. Out. Okay, and the next one is 3 -45. So we spin the angle 3 -45. So this time the radius is positive, but the angle is negative. So we spin the angle 45 degrees back this way. And wherever you stop, wherever that point is, just make sure that's a 3. Put a 3 right there and put a -45 here. There's a 3 on there. I don't care that it actually counts out 3 units. It's irrelevant as long as you put it there. And here you put a 1. Okay? So the actual length is arbitrary. If you want to get a ruler out and use centimeters every time or whatever, that's fine. I don't care. As long as you put the appropriate length on it where the point is, I don't care. It's okay.
I have a question.
Yes?
That would have been -3, -45, would you have just
It
shot
would have
that
been,
through
yep, it would have been up here.
and then it's like a terminal hole?
Spin the angle and backtrack through it. They're both negative. We're good? Okay. Now, before I move on, I want you to think about, let's think about this one here for just a minute. Shh. You understand that this point right here, as a polar point, is equivalent to 1 -pi fourths? They're the same. They land in the same place. Make your radius 1 and spin this angle right here. They're the same. It's also the same as -1, -5 pi fourths.
Yep, makes sense.
You spin -5 pi fourths, you land here. You backtrack 1, you land there. They're all the same point. You okay with that? Can you name another one? Is there another one?
-1, -10 pi-4.
Well, yeah, now we're getting into where there's billions of them. I want to stay in one unit circle. Let's see if we can do that. Let's see if we can name one other that's the same as this point right here. And here's what I mean. Take a look. We've got a negative positive, a positive negative, a negative negative.
Positive, positive. 7 pi.
Positive positive would be what?
1.
1.
7 pi.
7 pi-4ths. See? And they're all the same point. As long as you understand that, can reconcile that in your mind, you're going to be all right, unless this is not going to be a big deal to you. Is there anybody who's lost? Every one of these lands right here in the fourth quadrant. You good? David? Yeah, 4 points, all representing the same thing. So part of the exercise is going to be, it'll give you a polar point and it'll say, name this point 2 other ways. Or 3 other ways. Probably is 2. Okay, so you understand that all those represent the same thing. However, when we have an XY, there's only one way to represent it. You either go left or right, or you go up or down. Okay. All right, but there's 4 different ways to do this. Okay, let's move on. I want you to, I'm skipping a long ways ahead. I don't like example 2 at all. I think it's way too cumbersome for what gets accomplished, so we're not going to do it. I want to go clear over to the next page in the middle where it says coordinate conversion. This is where you're actually going to get some tools to convert from rectangular to polar and from polar to rectangular. That's a lot of what your exercise is going to be, is going from this form to this form and this form to this form. Okay? So I haven't done a lot of that yet, but we're going to now. I suppose it wouldn't hurt to put up here the words we use for these things. This, and I've used them enough, maybe you already know, but this is rectangular. Because every time we turn a corner, it's got a right angle in it. This is polar. In rectangular, the origin is the origin, and in polar, it's a pole, as I told you. Okay, now, take a look at the green box at the bottom of page 535, and it may be to your advantage to write some of this stuff down. It's not very much. Write some of it down, maybe in the top margin of your paper, so that as you're doing your homework, you only have to glance up instead of turn pages and try to find it.
I think that's a good idea.
You think I'm going to allow you to have a scratch paper like this on your next test? No. But for now, while you're doing this and getting used to it, it might not hurt to have it close by. But don't use it as a crutch for every problem. You need to start. And besides that, a lot of this is already stuff you know. Okay. If I have a rectangular point, the first quadrant, we'll try to keep it simple for a little bit. Let's say the point 3, 4. I'm going to go out 3. Up 4. Plot the point. So this is the point 3, 4 rectangularly. What would that be polarly? Well, to write a polar coordinate for this, we need a radius.
That's 3.
5.
Yeah.
Oh, it's Pythagoras.
Because this, if I were to draw a triangle there, and I will eventually, but if I were to draw a triangle belonging to that point, where I came down here and came out this way, I would have a 3 and a 4, 4 legs. Pythagoras tells us the radius, or the hypotenuse, which is the radius, is 5, because 9 and 16 is 25. Okay. What would be the angle then? Because I need an r, which we now know is 5. Pythagorean theorem told us that. What would be the angle that we whipped out from here to connect, that was to connect that point with the origin?
The inverse tangent of y over x.
Exactly, the inverse tangent of 4/3.
Good.
It would be the inverse tangent of 4/3 because the tangent of that angle is equal to the opposite 4 over the adjacent 3. Back over front. Vertical leg over horizontal leg. Would you all agree, or you see what's going on?
Yeah.
If it may make more sense if you actually draw this triangle that we've been drawing all along, where this is 3 and this is 4 and this is theta and this is r. It'll tell you. And if it doesn't tell you, I'll take either radians or degrees, but this is not going to be a familiar angle. If it's in radians, it'll be about 0.8.
Yeah, that's what I got.
What'd you say?
0.927.
I was going to say 0.87 something, but okay. All right. It's just slightly short of a radian. and I don't care, and you don't have to put a pi on it or anything, but you can give it to me in radians or degrees unless the instructions tell you. And if they do, then you better follow the instructions, because that's danger on the test when you don't pay attention. So you might as well practice it.
I got dinged on the last test.
Okay, so this rectangular form when we go to polar is equal to what? 5?
53.13 degrees.
All right. 53.13 degrees. Can you think of another polar coordinate since we're doing this? If I put -5 here, what would be the degrees for that?
-53.
Nice try.
233.13. No.
233? Yep. Because if the radius is negative, you got to have this angle to go with it, which is 180 degrees more than that one. Because theta's right there as well. It's vertical angles, right? Just for fun of it, can you think of one other? If I put a 5 in there.
Oh, I got it.
What if you made that 5 negative?
Negative 306.86
There you go.
or 87.
That's what I did in my head.
That one says if this is the point we're doing and it's a positive 5, which means I've already got the radius positive, perhaps I could use that angle, which is negative. And 53.13 degrees shy of 360. See what I mean? So there's different ways to do these. You get to practice it and stuff, but I just thought that I would just throw this in here too. There's only one way to name it rectangularly. There are 3. There's another one. You want to find the other one?
That's
We
-5,
have a positive, positive,
negative 126.87.
Yeah, it's gonna be different.
That would be using this angle, which is 90. No, which is 180. It's 53.13 shy of 180. That's the 126.87.
Yep.
Crazy. I know, crazy, but that's what you're dealing with.
Crazy problem.
Okay. Now, I still haven't talked to you about the coordinate conversion. Let me erase this. And let me show you another way to get this besides just muscling it through with this triangle. So let me remove this leg here so that we're just going out there like this. I'm not going to put the 4 and the 3 on there, although we have marks to indicate that that's how far out we went. Besides that, we have this. Take these off. Get back to the original. There is a way to find these 2 polar coordinates right here based on the conversions. And here's what we have, and this should make good sense to you. X is equal to r cosine theta. Right? That means that r is equal to x divided by cosine theta. Or the cosine of theta is equal to x divided by r. They're all different forms of the same thing. So if I stick with just this conversion, I also have this, but I wouldn't memorize these. You can memorize that, and then you can convert that to anything you need to for whatever you're looking for. That would be a way of finding theta if you knew x and r. This would be a way to find r if you knew theta and x. They're all different versions of this, yeah? Okay? It's also true, without writing out all the details, it's also true that y is equal to r sine theta. You knew this. You've seen this before. Do I need to show you again? Because I will. No? And the other thing is, that relates y's and x's and r's and thetas and all that stuff is this, which we use to find the 5. That is, x squared plus y squared equals r squared. That's also a conversion. But you already knew that. That's just almost instinctive to you. Also, this relationship, which we use to find theta here. This is how we found theta. We said the tangent of theta is equal to y over x. You've been using that as well. None of this stuff is new. And you may already have it committed to memory. I don't know. But they summarize them for you in that box, so they're all together there. This is what x is equal to. This is what y is equal to. If you know r and theta, you can find x and y. You can also find r and theta if you already know x and y. You can find r that way. And then x divided by r inverse cosine would be theta. Manipulate all of these things to find the conversions you need. So this is how you convert from one to the other. Those are the relationship equations. And they've got 4 of them. They've got this one, this one, this one that allows you to find r, and this one that allows you to find theta if you know x and y. Okay? Not that hard. So take a look at example 3. It says find the rectangular coordinates of the points with the given polar coordinates. So we got polars. We're going to try to use these circled conversion factors. I'll leave them up here. We're going to try to use those to find the rectangular form of this polar point. Polar point is 3 and 5 pi 6. Now, I, myself, personally, in my brain, am extremely geometrically oriented. As soon as I see that, I know it's in polar form, I immediately draw a picture. You don't have to. You can use these conversions if you want. What we're looking for is an equivalent form, a thing of the form xy. Well, look, I can find x by taking 3 cosine of 5 pi 6. And I can find y by taking 3 sine of 5 pi 6. What's the cosine of 5 pi 6? Do you know that? Without your calculator.
30.
I want this in terms of pi, since 5 pi, I'm sorry. I want this in terms of things you know, since 5 pi 6 is a familiar angle, I want this in exact form, which means radicals. Do you know the cosine of 5 pi 6?
3 over 3.
Negative root 3 over 2.
Yeah.
Now, if you're figuring, you're going, I don't, now's a good time to draw a picture. I would have drawn it before now because I'm so geometry oriented, but 5 pi 6 is a pi 6 short of pi, right? So it's out here with a reference angle of pi 6. The radius, well, I'm not really deal with the radius. For right now, our picture's going to have a radius of 1, which is what we're used to. You remember that if this is 1, that this leg right here, the long leg, is root 3 over 2, but since it's left, it's negative. And this is 1/2. So what I'm saying is when this is 1, the cosine part of this, just this part right here of this conversion, the cosine of 5 pi 6 is negative root 3 over 2 times the radius 3. So it's negative 3 root 3 over 2.
You have to keep it in radical form.
Yes, if this is a familiar angle, you do. And it is a familiar angle. What is the sine of that very same angle?
What?
1/2
So the
times 3,
halves.
3/2.
Triangles? Yeah.
You okay on that or not really? So it does help to draw the angle and even just make this a 1 so you can remember the things that you've learned so far about cosine and sine and then multiply them by the radius. There's another way to do this too. And that's to make this 3 directly and remember your geometry from when you were freshman. If you don't want to do that, then do it this way I just did here. This is an option right here, it's great. Make this a 3 already. Since this is a 30, 60, 90, this leg right here will be half of the hypotenuse. And this leg right here will be that short leg times root 3. But it will be negative because it's a left one. So if you remember your geometry and remember the relationship on a 30, 60, 90 between the hypotenuse, the short leg, and the long leg, you can get these directly. If not, go back to what you've been doing lately, which is letting the radius be 1 and get these back. Then multiply those things by 3. You with me there? Either way is fine. Draw me a picture. I'll be able to follow it either way. Okay, let's take a look at the next one. 2 and negative 200 degrees. So I'm going to erase this and keep these up here. So I've got the polar coordinates. What did I say? 2 and, is it 2? 2 and negative 200. Would you like to draw a picture just to get an idea where things are going? That's what I always do. So I spin the angle first, which means I'm spinning it backwards. This is 180, 200 is right there, degrees as the reference. Right? Did y'all see that? So we're at this point right here. We want to find that rectangular one. So it's going to be a negative positive point. Your second quadrant. Do you want to go ahead and call this 2? I would, because this is not a familiar angle. Just go ahead and make this a 2.
Okay.
Find it directly. So to find the x coordinate of this point, we would take 2 cosine negative 200, or if you want, positive 160. I don't care either way. It doesn't matter. Your calculator. Just make sure you're in degree mode. Just switch to degree mode before you start calculating if it's in degrees. So take 2 cosine negative 200. Since this is not a familiar angle, I, as a teacher, have to accept decimals, which is fine. To the nearest hundredth would be great. Now, do 2 sine negative 200 in degree mode.
0.68.
There you go. And that feels about right. You're going to have to go a long ways out and not very far up for a 20-degree angle. And it is negative positive, so you're good. Y'all clear? If this angle is a familiar one, I expect it in exact form, radical form. If it is not a familiar one, then all bets are off, and make sure you round to the place that they tell you, if they tell you. Okay, let's go backwards now. Let's go from rectangular to polar using these things. So we're doing example 4 right now. It says find, now notice the instructions. It says find 2 polar coordinate pairs for the points that are given. So we got to find, because polars come in sets of 4, even if one go around the unit circle, they come in sets of 4. We're supposed to find 2 of them. And the rectangular point that we're doing on the first one, I think, is it 1, 1?
Negative 1.
Negative 1, 1. What quadrant is that in?
Second.
Second quadrant. With a reference angle of what? Can you tell? 45. A reference angle of 45. Because if the legs are the same length, which is what this is,
Oh, that's right.
it's got to be a 45, 45, 90. But this is how you would start. You go back 1, up 1, put a point. We want a polar coordinate for that. So that's when you start drawing triangles this way from that point. And if this is 1, negative 1, and this is 1, since the legs are the same length, this has got to be 45 here, which makes that 135, or 5/4 and 3/5. Yeah? Okay. So what is one polar point? What is one polar way of writing that point? Can you think of one?
We don't have
Then a 1.
Oh, we need R. Well, then go to this.
Oh, it's for 2.
It's for 2, isn't it?
Yeah.
Okay. So we've got R. Now we need theta. We already discussed theta. That's how we drew the thing. 3/5, which is I like that best if it tells you in radian. 3/5. That's one way to name it. Can you think of another?
Negative 5/4.
Yeah, that would work with a positive root 2. A negative 5/4 would also get you there. Just to continue practicing this, what's one with a negative root 2 on it?
Negative 5/4.
Negative 5/4. Because you would have to spin it along to here and then go backtrack through it, right? And this is negative 5/4. What's another one with a negative 2? Negative root 2. Negative? 7/5. Positive. Because we could spin it this way and get on that one and then backtrack through it. Any of those two, because it said to get a pair, any of these two will work. Okay? We clear or not really? Okay. One more. Let's see. Let's do a quadrantal angle, negative 3, 0. Ooh, we haven't done one of these. Let's see if we can reconcile this. So the rectangular is negative 3, 0. Would you like to think we should graph that?
Always.
I think we just swap them right in the equations there.
Good. What is one rectangular coordinate for this? Use degrees this time.
It'd be 3.
Polar. Polar that belongs to this rectangular.
R is 3.
Yeah, R is 3. What's the angle?
0.
Pi. You said pi. I'm asking you to do degrees.
Oh,
1/8. Just for sake of variety, since I'm only looking for a pair, what would it be if I had -3? What would the angle be? 0. Because you'd have to come out this way and then backtrack through. And what angle have you spun out here? Haven't spun anything.
So could you do
Wow,
60?
trickiness, Jay.
Can you do another one just for the sake of variety here? Can you do another one that's positive? Positive radius?
Negative 180.
There you go. And what if do we have another one that's -3 with a -3?
Negative 0 degrees.
Or
360.
360?
Negative 0
degrees.
Okay, do you think you can handle this? Does this look reasonable? Because this is all there is for today. These are all polar. This was rectangular that we converted to polar, using degrees for the theta. Okay? That's all, basically all you're doing. There are 17 problems. It should not kill you. I think you're gonna be okay. Good luck.
I thought it was gonna be able to see all the other options.
See ya.
Yeah, well, you could have